So continuing with our detour into how we just try to see what are the philosophical foundations of quantum mechanics. So in this class we are going to see how so I just write a statement of Heisenberg. So since it's philosophy of quantum mechanics, so what we observe is not nature but nature exposed to our method of questioning. So in this background, we can just see this thing. So observance. So here implicit in this thing is that is a philosophical principle of maybe duality. We are observed and observer are distinct. Or distinct. What we observe is not nature, but nature exposed to our method of questioning. So, what is out there is an objective reality, which we might think that it's innately true or it's innately out there. It's an abstraction, and it further gets compounded or complicated by the very act of measurement as a quantum from the point of view of an observer, a quantum mechanical observer, how we construe observer in the quantum mechanical sense. Even though these two statements may be in some general sense, but when penned down against realities which we can infer from quantum mechanical realities, they have relevance. So, in this sense, if we come to the fourth part of the disturbance of object by observation. That's the point. So whether the observation is going to disturb this object in some in some controllable ways or in some non-controllable or non way, that there is always an element of uncertainty or ambiguity or there is element of inadequacy in as far as our faith in that complete description is concerned or our objective description is concerned. That's it. Prior to or after the observation has been there. So this is the fundamental thing. So the import of the Heisenbergian discovery is that indeterminacy of all measurements is a consequence of disturbance by means of observation. So that's it. So now there are a couple of observations made here in the book that whether when we import some sort of indeterminacy which is supplied which is somehow allied to the idea of when we observe something, whether that indeterminacy is part of measurement or it's somewhat intrinsic to the system. That's it. So, for example, a thing in itself. So, things in itself and things as we measure. So, this is again another thing. What are things in its so relational aspects of things? So, whether our measurements, which is relational in that sense, that describes that's the way we define a system, rather than defining the system in some absolute objective sense. That's the way. So the thing is that so these so for Reichenbach, all these statements have to be made with respect to taking observer into consideration. So it should not lead the idea of observer should not lead to a sort of a mystic or a sort of doing away with the problem. But it's merely the difference of classical observer and quantum observer is that in the quantum observer, an observer cannot interpret the causal chain, the effect and cause in some exact sense. But the presence of observer is as much important in the classical world as it is in the quantum world. It's merely the quantification of those measured quantities which will lead to some sort of this thing, or the disturbance, which is which you may associate with the observer. It leads to some. It leads to something, and this disturbance does not. So this disturbance should not lead us to something effects related to some subjective aspects of the observer. Observer, in intrinsic sense, doesn't have something as a value in it which will change the measurement of observer in that observed in that strict sense. It's the act of measurement on account of the observer which leads to a disturbance, which leads to a measurement which is controllable in the quantum mechanical sense, and you can control it in some classical sense. So here comes so what for Reichenbach is. So here is a viewpoint of his quantum mechanics, how he sees quantum mechanics. So it's his personal view. There may be other views also. So first we'll state his view, what he says. So quantum mechanics should not be misused for attempts to revive philosophical speculations which are not on the level of clarity and precision of language of physics. So the misuse of philosophical speculation, whether the observed and the observed cannot exactly quantify things. Should it lead to some mysticism, or should it lead to some fundamental inadequacy of trying to determine things in that sense? So it has to be done. It has to be So you have not to take seriously the things. So the language of physics, the vocabulary of physics for 300 years, so it's still relevant, and the precision we are going to use. So for him, the philosophical problems of which problems which quantum mechanics implores us to address should be addressed within the scientific philosophy, uh, and maybe symbolic logic. So here maybe I'll say a couple of comments. One comment rather. There maybe the times Reichenbach was living in. So it was a pinnacle of the way Russell and the logical positivism and the analytical philosophy has and empiricism. So he's basically trying to just localize quantum mechanics within that sense, the influence of logic and influence of scientific philosophy, which is primarily an empirical way of looking at things, which does away, which doesn't in its basic frame take any subjectivity of the observer, subjectivity of observer, or even though the measurement is taken, but is to be not taken into consideration. That's it. So even though world is not, the act of measurement leaves a world which you cannot be said objective in that classical sense, but that faith in that objectivity is there. Now, so the next question which you can say, which is being asked, is that why is it not possible to apply this logical procedure, which logical procedure to quantum mechanics? So which logical? First, I'll say which logical principle. The logical principle is that of that uncertainty of predictions is a consequence of disturbance by means of observation. So uncertainty of predictions is a consequence of disturbance. Uncertainty of predictions is a consequence of disturbance by means of observations. Why uncertainty of predictions is a consequence of disturbance by means of observations. So question is, why is it not possible to apply this logical procedure to quantum mechanics? That's it. For example, if you want to measure temperature of the room, the temperature of the room can be measured by thermometer, but or water. So the question is temperature, the instrument by which it's going to measure temperature, the measuring apparatus. For example, thermometer has its own temperature, so we will not say whether the thermometer in itself has some role in increasing or decreasing the temperature which you are going to measure. For example, room or a bucket of water. So the instrument becomes very much important by which we are going to measure things. So the role of instrument or role of the observing apparatus. So we just somehow in the classical sense we just assume the measuring apparatus. We can subtract or mod out the effects or even account for those effects in some suitable experimental arrangement. But that thing somehow is we cannot that logic somehow seems not to be working here in quantum mechanics. That's what I'm saying. So whether that logic uncertainty of predictions in the is a consequence of disturbance by means of observation, because in the classical sense that disturbance can be accounted for or modeled out for, whether added or subtracted at the end of the system. We can see what was the temperature of the thing, but we can temperature of that thermometer, and we can add or subtract that thing in the scheme of the measurements. But even if we don't take that instrument has some temperature, we can just say it's one of the observation. It says something about how we measure a system, even though it may not be that accurate. Or it's one of the system, or it's one of the measurement of that ensemble of the system, one of the measurements, you can say it. So in the Heisenbergian cross-sectional law, where we say that these are two conjugate observables which may have different causes. The effects, those effects can be traced to one same or different causes. How those are related? In the previous class, we talked of Heisenberg's uncertainty principle in terms of cross-sectional of parameters, where the interpolation of observation vis-a-vis observables, whether it was possible or not. So in the same sense, the Heisenbergian, which says that correspondence, positions, corresponding for observational case, for how we just observational results. So corresponding distribution of position and momentum must be derivable from a psi function, and therefore they must be correlated. So you can say the measurement of position involves physical measurement of a kind related to the observational effects of the process. That's it. So here comes the one important thing, which we can say in quantum mechanics how it's different from classical mechanics. So this sentence will make So in Heisenberg's scheme principle, we can be formulated as we have no exact knowledge of physical state, physical states, because observation disturbs things in an uncontrollable way. Yes. So this is the crux of this thing. So the observation, in the classical things, the system, you could disturb the system in some controllable ways. In the formulation of uncertainty principle, the word uncontrollable comes. So that leads to sort of uncertainty. Whether we can quantify that uncertainty, or whether that uncertainty has to say something about the causal indeterminacy of the universe. Quantum mechanics is indeterministic, and whether world is objective, whether observed duality. So there are a lot of questions. These are the effects, and it implores us to question those very assumptions which we take given in the scheme, in the previous scheme, things. In the scheme of empirical philosophy, in the scheme of objective, scientific objectivity, in the scheme of logical analysis, positivistic way of looking at things. Now the important point is how we can, so if it is this thing, so it asks us how we can observe the unobserved, how we can or determination of unobserved objects. So it further asks for us how we can the unobserved can be determined. So before we are going to analyze a particular situation of the unobserved thing, for example, there are a couple of statements. For example, so if something you want to say, for example, there is a good example here in the this book. So I am going to rephrase it. For example, there is a tree which is so you have always seen a tree outside there in the garden, whenever you look at it. So whenever you look at in the garden or outside this glass, you will see a tree. So whether tree is out there or not, or it is contingent on this fact that it depends upon the fact that the observance of tree is possible only when you see the tree out. So whether tree is out there or not, so it can have both. It's always out there, or it's contingent on my observation when I see through this glass. How can I verify that the statement is true? So I have to see other people also observing the tree in absence of me observing the simultaneous my observation. So if they also can confirm it, so then we can say the tree has been always there, independent of whether I am observing it or not. So again, here we are going to generalize from an inductive understanding of things. One person is seeing, two persons is seeing, so n persons are seeing. But nobody is also seeing. Nobody has seen the tree out there, but tree may all still be there. So individual observer being seeing a tree two or more observers conferring the tree independent, the existence of tree outside, whether one is seeing or not, other is seeing. All persons seeing the tree, or nobody seeing the tree. When there is no observer, the tree should be out there. So these are two, three, four ways of looking whether tree is out there, or it's my perception of looking at outside. I am able to see, observe a tree. Or there is an indirect way of saying it. For example, if I have seen this thing, a man is not out there, so I can, his shadow can give me an inference that somebody is out there standing. Standing, his shadow. If there is a shadow, I can say that inference of shadow will say that it's the person is out there. So the question is whether something is out there. It's contingent on the fact, my perception of what I'm going to observe. Is it dependent upon that the thing there is basically I am seeing it. So whenever I see things from that side, I see its presence there. So it has always been there, or it came out after my observation. Or I can verify it by some indirect inference. So these are the things, indirect inference or by inductive inference. For example, I'll test case by case if other people also have seen. So simultaneous observers confirm a given inference. So why I'm just talking of these things is that we can say so how we can so either it may look nonsense, but at least we can we have to quantify our ignorance or presence of a given event which is out there. So these are all things. So, but how is quantum mechanics coming into it? So we will say that so there is there is more than one true description of unobserved objects, which we call as class of equivariant descriptions. So where observable things descriptions can be admissible as well as inadmissible. The way we filter out data and ultimately reach to something concrete. In the same way, what are the admissible, what I should say, the descriptions and the inadmissible descriptions. So if we try to frame this very thing in terms of how the role of observer becomes important in quantum mechanics, in the quantum world as compared to the classical world. So our understanding of the world may be like we can just have two principles, that laws of nature are same whether or not objects are observed. Second, states of objects is same whether or not objects are observed. So this is a sorry, it's a classical way of looking at things. Laws of nature are the same, whether or not objects are observed. So there's an objective description of reality out there. Whether an observer observes or not, that's besides the point. Or states of the objects are seen. So whether the objects are, so even the states may change after observation, but the states are there and they are uniquely, they have some unique value out there. And this is in the normal scheme of things, it's the way we define a normal system. This is the way we define a normal system. So this description comes under stress. It comes under this thing. We just have to just speak the validity of these two postulates vis-a-vis quantum mechanics. How we have waves and corpus humulus. Wave. So it's no. You might be knowing the historical debate of whether wave of light was wave or particle, and it passed through different things down to 20th century, where it was neither wave nor other particle. Some set of experiments say that it's wave, some say it's a particle. So we can have two things. What should say? So we have two occurrences. So observables of all occurrences which happen between coincidences, such as movement of electron or a light ray, and we call, so if events happen by coincidences, for example, movement of electron, light, so we call this phenomena as, and so we're going to classify phenomena as interphenomena. And interpolation, the way we also previously said, interpolation, it means an act by which the observed and observer are interrelated by some inference or by some inductive inference. That would be the proper, by some inductive inference or by some inference, we can relate observer and the observed. That's it. So if it's that way, so what we are going to say is, so when we speak of corpuscles, but once we speak that in terms of quantum reality, we don't talk of wave packets, we talk of probability wave. So we rather say of probability waves as laws of probability framed in terms of waves. So, and we know that so when we talk of particle and wave, the idea of just binary of localizing things and delocalization. Particle is associated with localization, you can pin it down, and wave is associated with it has an intrinsic, it wants to spread, the disturbance moves away. These diabolic features of localization and delocalization are somewhat contained in that wave particle duality. So we have to impose probability descriptions has to be seen through uh, in terms of we say that matter consists of particles. Matter consists of waves and this is one interpretation. The other is particle interpretation is that corpuscular interpretation is what according to which matter consists of particles controlled by probability waves. Or we can say that waves have a thing behavior. So waves have a thing behavior or a thing character or a behavior character. The thingness, and when you have things, you have an element of not say eminence here. So it's a more tougher, heavier English word, thingness, and the behavior has an element of transience. It has some sort of expansivity in it. So you want to localize something, and it's simultaneously having a delocalized character. That's it. Now here. There is this thing. This thing has been famously articulated by Bohr-Schrödinger complementarity principle, that once in the when the observer is going to pin down two observers, two events. In terms of particle and the wave character, one measurement becomes fuzzy at the expense of other. You measure wave effect, the particle effect becomes fuzzy, and the particle effect is measured precisely, the wave measure becomes that much inadequate in any given experiment. So again, it's this Bohr's complementarity principle. There can also be another principle. So in Bohr's complementarity principle, then observer, when he tries to quantify or measure two events, two aspects of matter, whether wave aspect or the particle aspect, so there is an intrinsic or inadequacy to exactly measure things in a given experiment. It will concentrate on the wave aspects more, the particle aspects become imprecise, and vice versa. So against this backdrop, there is also a state that you know, but there is another which this has talked, Land's his principles of quantum mechanics. So he says that instead of saying that they are complementary, one at the expense, one measurement at the expense of another measurement, we have to say that all experiments can be measured, can be explained by both interpretations. That will never be possible to construct an experiment which is incompatible with one or the another thing, one or the other interpretations. So rather than having one variable at the expense of another, precision of measurement of one at the expense of other, we have to be think that we have to take that both of the interpretations are true. And in any given experiment, you cannot show one is not true or other. This is the other way of stating quantum mechanical reality. It's as if a statement of another statement that a great truth has an opposite, which is also a true statement. So we can have so that's it. So that's the point. So now at the end, so there's a bit of statements which I'll write, and I just talk of my comments, couple of comments, my own thing, how I see it. So Reichenbach sees it that there is a synthetic, there is a, so we cannot admit he is. So this leads to our inadequacy of what I should say. So these statements. So Lane's statement is, although it's a statement in the way we have Bohr's statement, Bohr complementarity, but since it's mostly in textbooks, we talk of complementarity in terms of some inadequacy. In the background of that classical deterministic sensibility or methodology. So in the same this Reichenbach is also just echoing it. He is not taking Lane's statement. So from the epistemic considerations, so there we cannot there is we cannot admit what he is saying. We cannot admit a synthetic the synthetic a priori principle which is not logically empty, which is not logically empty, and which physical theory is bound to satisfy, which physical theory satisfy. And the other remark is whether if there is a such system, so the question as an experience is that normal system can be normal system can be answered by that experience. So what he is trying to say, so he's talking of a synthetic a priori principle. So whether the way Kant's critique of pure reason, we have a synthetic and so judgments and analytical judgments. So the endeavor of knowledge is basically a synthetic a priori statements which will express those words. The synthetic a priori statements may also, some portion of it may be mathematical statements, but some part of it may be the empirical aspect of the world. So both of them should construe for us experience. So in absence of any, we cannot pin down variables in that exact sense, in the classical deterministic sense. We cannot interpolate the effects of observables for two simultaneous conjugate variables to some common cause or to a common causes from which those effects can be traced to in some exact quantifiable sense. It asks some fundamental questions about what we talk of objective world experience. Can there exist synthetic a priori principles which corresponds to that thing? So if we are not able to quantify things in the exact and precise sense, so our synthetic faith in that synthetic prior judgment of things stands to question. So that's the point. And further, whether that experience may be complicated. So, and that experience part of it. If knowledge comes through only experience, so that's it. So whether things will be simple or they will be complicated. So whatever. So what by no means it's permissible to refuse an answer to the question as meaningless or to evade it by drawing attention to other sides of the problems. So I'll just maybe so this is the important thing, whether a priori synthetic judgments which describe the world can be that reality can be also that epistemic justification can be there for the quantum mechanical interpretation of things. The imposed understanding of quantum mechanics, the epistemic understanding of quantum mechanics, the epistemic foundations of quantum mechanical understanding of things, whether that can be rooted in those synthetic a priori statements or judgments. Before we can speak of whether the duality of observer and observer at bifurcation is still there. Uh, so in the coming classes, we are going to just discuss thread in detail. Thanks for listening or seeing it.